speaker, Zofia Taranu. So Zofia did her master's and PhD at the biology department at McGill University in the lab of Renée Gregory-Eves. And in 2014, she started a postdoctoral fellowship at the University of Montreal with Pierre Legendre. And then she received another fellowship to do a second postdoc, which she did at the University of Ottawa with Francis Pick. And since 2019, Zofia is a scientific researcher at the Aquatic Contaminants Research Division at Environment and Climate, it's a mouthful, Environment and Climate Change Canada. And the talk she will present today is entitled Detecting Critical Transitions and Signals of Changing Resilience from Paleo-Ecological Records, a Multivariate Approach. So without further ado, I will let Zofia share her screen and get started. As I said, there will be time for questions at the end. You can also write in the chat if you have questions, and we'll look at the chat at the end. So Zofia, the floor is yours.
Great, thank you so much. Yeah, thank you, Marie-Ève and Trisha and the whole group for the invitation. It's really great to be here, and I'm looking forward to just discussions and future maybe collaborations even. So yeah,
Zofia, before you begin, just want to switch maybe your, we see the presenter. Yeah, just. Okay.
Now is it okay?
Nope, not yet.
Okay, hold on. I think I know what happened. How about now?
Nope. Or maybe
you know
just start over if you want.
Sorry about that. I think I clicked on the wrong screen.
Mm-hmm.
Okay. How's that?
Yeah, perfect.
Okay, good. And then if I move this here, you guys are still seeing the presenter view?
Yeah, we see the proper
okay.
one. Yeah.
Okay, here we go. Okay, yeah, so basically today I'll be talking about a project that I worked on with colleagues, so Steve Carpenter and others from Page's working group on critical transition, where we were interested in whether or not we can detect critical transition from paleo-ecological records. So I'll spend most of the talk on that, and then I'll end off with more recent work where we're trying to extend the approach from a univariate model where we just look at one response to a multivariate where we could look at community responses. So just to give an outline of the talk, I'll first just provide a bit of a background on regime shift and critical transition theory, then the motivation for applying it to paleo records. And to do that, I'll spend a bit of time on how we simulated records to mimic, or simulated time series to mimic paleo records. And we did this because we wanted to be able to test early warning signals of indicators that are typically used in the literature and see whether or not we were able to get back what we put in. And also then we use these same simulations to test other methods that may be more appropriate for paleo records that have certain biases and are not completely comparable to monitoring time series data. Then I'll just end off with that project or that paper by presenting an application to a few real cores or time series lake cores. And then I'll end off with presenting the multivariate approach that we want to develop or is developed but we want to apply, and really moving to what was the goal all along for this this working group or this project was to have what we call the many lakes, many proxies paper. So applying this at a broad spatial scale and across different proxies. And then just provide a bit of a future outlook in terms of what's left to do for this project. So just to provide a bit of background on regime shift and critical transition theory, I thought this might be a good way to start off the talk. So I think there's two key things that are important to really set off from the get-go, is that when we're talking about continuous time, we see in the literature that a critical transition occurs when the dominant eigenvalue, which is also means the rate of change of the system, goes to equilibrium, goes to zero. So basically, when the rate of change slows down and the system becomes increasingly slow in recovering from small perturbation, we have a critical transition. And so there's really nice math behind this that could show how when your eigenvalue or your rate of change is negative, we have a stable conditions, and as it increases and goes positive, then we have kind of a catastrophic change. And the reason for this, without going too much in the math, is that somewhere in the equation of this time series dynamics, there's e to the lambda, where lambda is the eigenvalue. And so we could see that if the lambda is negative, your system will go down with time to zero. So it won't explode. But you can see that as your exponent becomes positive, then your system could really explode. So this is for continuous time. But then we can also see literature and present the same question in discrete time. And discrete time is what we usually do when we sample at different points in time. So in discrete time, we have a critical transition when the eigenvalue actually approaches 1. So instead of 0, now we're talking of approaching 1, which is a key point to note, because in reading the literature, some articles may refer to a critical transition when the eigenvalue goes to 0, and other papers may say 1, but it depends on which time are they working in discrete or in continuous time. And so the reason for this, there's a nice proofs behind this, but it's essentially because we're mapping into a different world where your eigenvalue is as long as it remains within a unit circle, you have stable condition. If it exits the unit circle, then you have unstable condition. And part of the way to explain this is that when you're going in discrete time, the way to get from time 1 to time 2 is that you multiply the 2 times together. And this multiplication makes it that your lambda are being multiplied by one another. And so this just changes the condition at which your lambda will explode. And so for me, this was something that I found really hard to get my mind around, but I recently found a 20-minute YouTube video that explained this extremely well. So I could share this if you're interested in the math behind it and just understanding why this actually holds. So with that, if you feel good about this and regime shift theory in general is you're comfortable with, then maybe in the next few slides it's a time for a coffee break, because it might be a bit repetitive or something you already know. But if you're like me and you feel so about this, or you need a refresher, just stick around for the next few slides, and then after that I'll really dive into to the paper. So just to keep in mind, a critical eigenvalue is different in continuous versus discrete time. And so in discrete time, so most theory that we read or theoretical papers are in continuous time. So you'll see those papers saying it goes to 0, whereas real world ecological data occur in discrete time. So in general, theoreticians use continuous time because the math is less cluttered, whereas data people use discrete time because real world lives in discrete time. So even though the math is more cluttered, they just deal with it with their coding. So for this part, for the paper that I'll be presenting or study, I had the chance to work with a great data person who wrote amazing code. So all of the figures and all the models are in discrete time. So you'll see that when I talk about going a critical transition, you'll see that rate of change or that eigenvalue goes to 1 in the figures, and that's an indicator of a regime shift, of a critical transition. Sorry, but before going into those examples, I just want to spend a bit of time on the theory. And so because we're working with theory, we'll work with continuous time. So with continuous time and with the eigenvalue going to 0. So the theory says for in continuous time, if you have in a linear system and you have something affecting your system state, so a condition, an environmental condition. You can have a shift in the system if there's a large external change, but this will result in a linear response, even though the forcer is large. You could have conditions where you have a non-catastrophic threshold. So here it's not a critical transition, but you have a threshold response where you have a small forcing and it causes a large change across the ecosystem. And then you can have the scenarios where you have what they call the fold in your equilibrium curve. So your curve is actually folding over, and you can then see that there's 3 different equilibrium points that appear. And so here you could see that if you're on the arrows, on the dotted arrows here indicate where you go if you're nudged off a little bit from the equilibrium line. So if you're nudged off of this point, you come back to the equilibrium. But if you're on the dotted line, you're in an unstable point. And if you're nudged from this line, you'll jump from one state to another. So you could also think of these as your valleys and then this is the hill. So if you're on the hill and you're nudged over, you'll roll down pretty quickly to your valleys. Okay, so that's just repeating what I just said, sorry about that. And then one other point to remember is that if your system is close to a bifurcation point or this tipping point, if you just have a tiny change in the condition, you could jump from one stable state to another. And so this is really important because if you're going, let's say your condition is increasing nutrients or like eutrophication. And so if you're increasing your phosphorus and you're suddenly go past a certain point and you jump from a macrophyte dominant state to a cyanobacteria dominant state, what this theory indicates is that if you want to return, if at all, to your prior state, you really have to reduce your phosphorus to almost an oligotrophic state. And then maybe you'll be able to return, but it's not a guarantee. You could also have cases where you just have a small noise or stochastic variability that causes you to just jump from one state to another. And in any case, all of these different scenarios, you could see if you apply early warning signals, such as rising autocorrelation or variance, you could see a change in the ecosystem, an indicator of a change in the ecosystem. So I just wanted to spend time on one of them, just to get back to the whole lambda question that I brought up earlier, or the rate of change. So I'm just going to rotate that figure a little bit to be able to really see the slope, which is the rate of change of the system. So if we start at a point that's on the equilibrium point part of the line, and if we increase the condition, so if we set that value, the slope is negative. So here lambda is negative. And we remember that from earlier that if lambda is negative, you're in the stable area. But then as you increase your condition and you move along this equilibrium point, you will eventually get to where your slope, so this is the point here, is 0. And so when the slope is 0, the rate of recovery, which is lambda, is reduced. And this rate of recovery is actually a proxy for the size of your basin of attraction. So basically, when we started off at this point here, we had a nice big wide basin of attraction. So if we were nudged in one direction, we came back. But then as we move along, then if we get nudged, our rate of return is small, and it tends to 0. So if we get nudged, we are less and less likely to go back to our basin of attraction. And so just to really drive this point home, and then I'm done with the background. If you have a high resilience system, your basin of attraction is wide, is very large. And your rate of recovery is fast. So if you get pushed up the hill, you'll come back really quickly down to the valley. And if you look at early warning signals in this scenario, you'll see that you don't have a high correlation between time step 1 and 2 because you quickly return. So there's the value that you had here is very different from the value that you had in the valley. If you're in the low resilience scenario, and your basin of attraction has been kind of eroded away, it's very small, and now your return rate is really slow because you're basically moving along a plane, so you're a flat area. And so in this system, the correlation is very high because where I was 1 moment ago is really strongly related to where I am now because I'm moving so slowly. Okay, so that's done with the theory. So now we can see why when we look at theory in continuous time, if your rate of change approaches 0, then you have a critical transition. So if lambda goes to 0, you have critical transition. For the examples that follow, we'll be working in discrete time. And so here the rate of change goes to 1. I won't go into showing the math behind this, but kind of just a bit of a leap of faith that in this, there's proofs that show that we're going to follow lambda going to 1. Okay, so moving on to the motivation for applying all of this wonderful theory to paleolimnology. So I think many responses of aquatic ecosystem, as we know, extend beyond the monitoring record. I think this is one of the key things that we, like paleolimnologists, all say at the beginning of a talk to set the grounds for why paleo is so important. We need to see beyond when actually the changes started to take place, because we tend to just arrive at a site if it's already has been in a eutrophic state, for example. Also, another reason that we were motivated for this to look at paleo is because there was increasing skepticism about whether or not these nonlinear responses are the exception rather than the rule. So is it really something common, or is it just a few cases that we happen to go to because they have a change in state that was observed? And so really to get to these points, we needed to consider longer time series and higher resolution as well. And we also needed to look at a greater number of lakes, so many different lakes across the globe. So by using sediment cores, though, there are certain biases that we have to think about, such as core mixing and core compression, which may have consequences on the statistics that we commonly use to detect critical transition. So because of this, sediment cores are not strictly analogous to instrumental data. And so there's really a growing need to verify the methods, but also maybe even develop methods that could be used to detect regime shifts in paleo records. Critical transitions in paleo records. So this brings us to the next part of the talk, which is the simulation where we try to create core records. So here, the gap that we're trying to get to is to see whether or not we could use core records to test for critical transition. And to adjust this, we needed to build a model of core formation and then define the conditions under which we can detect what we put in. So we simulate data that have regime shifts, or sorry, I keep calling regime shifts, but I mean critical transition, and some that we know that don't have, and we try to see that if we can get back what we put in. So the first step for this was to generate time series of lake dynamics using a eutrophication model. So as you increase phosphorus load, the lake becomes more eutrophic. And then we modified this the ecosystem to more accurately reflect sediment core archives by including sediment noise within the model. And then once we had this model, we generated 1,000 years core archive, and then we subsampled it within 400 years to look at a window of 300 years prior to and 100-year post an estimated tipping point. So this represents a really longer core series that I tend to work with. I tend to work with 200 years about, but it was just really to have as much a data-rich time series. So just to talk about a little bit about how we the noise and that we added in the lake eutrophication model. So in that model, they already had parameters to estimate the variance in an environmental noise, so within the water column, but we needed to add the noise within a sediment core. So to do this, we cross-examine the literature of pigment stratigraphies or sediment core archives from about 100 lakes, and we looked at the coefficient of variation, so how much the pigment of interest varies over time. And so what we saw is that in general, when you were an oligotrophic lake, it didn't really vary that much. So the variance was generally well below 0.5. But then as you increased and eutrophication increased, then the noise and the variance also increased. So this is just to say that it gave us a range of natural conditions by which we could play with our model. And as we increased phosphorus in the lake, we also increased the noise in the sedimentation. So this allowed us to create these different numerical experiments where we had we loaded the lake with phosphorus, and then we looked at the P mass, the mass of phosphorus in the lake water, and also in the sediment archive. And we were able to see, okay, when do we see, at what value do we see a regime shift? And so we were able to detect at what value we needed to increase our parameters in order to get a critical transition. And so far what we've seen is a model where we have a time series, and we have added noise to reflect some of the different noise that's occurring in the system, but we still haven't converted from the time domain to the core domain. And to do that, we needed to add core mixing, which mixing within the sediment core could happen as we just take the sediment core, or it could happen because of bioturbation. So that means that intervals that are close by may be mixed together. And there's also the really important point that core compression is taking place. So we know that as cores, as sedimentation goes on and we move down the core, there's more and more core compression, and that this also varies depending on if it's a eutrophic lake or a oligotrophic lake. So the rate of sedimentation varies. So first, with mixing, we assumed that there was a standard unit normal distribution where mixing occurred among approximate core layers. And we then tested different scenarios of no mixing, so represented by bar core, medium mixing, and high mixing. And the window or the standard deviation that we used, we based it on the literature where there were some studies that used trace metals to see how much they, they spiked the sediment and they saw how much they could spread throughout a core. It was older literature, but it was still very useful. Then for core compression, we analyzed age depth models to relate the years per centimeter to core age. So we wanted to see how much the chunk of year, how many years per centimeter happens and how this changes and compresses as we move down. And so relate that thickness to the age of the core. So this relationship varied among lake types depending on eutrophication. And so we generated scenarios based again on the literature where we had low, intermediate, and high compression. And we did this by varying the intercept, A0, and the slope A1 that we obtained. Again, this is just the histogram showing what we found when looking at the literature when we related these two variables across different cores. Okay, so I just wanted to recap what we have seen so far. So we saw that we simulated lake dynamics using well-known or published lake phosphorus loading models. And then we simulated from that core record by sampling that record, but also adding mixing, compression, and environmental noise. And we parameterized this by using, by analyzing age depth models from real data, and also analyzing the variance or the coefficient variation of real data. So then this brings us to testing our question of these resilience indicators. Are they able to retrieve what we put in, or do we need to move to other models such as these state space models, which I'll get to later. And then for all of these different scenarios, so we generated scenarios of no regime shift, no critical transition, all the way to high noise and flickering scenarios. And then we also played around with whether or not there was low to high mixing and low to high core compression to just represent different kinds of cores we might sample. So now getting to the results that we had for the rolling window resilience indicators that are typically been used to test for critical transition in the literature and have worked really well with monitoring data. So with rolling window indicators, it's common to approximate the behavior of the eigenvalues, so the rate of change and how if we are in this like shallow basin that with a slow return or in a steep basin with a rapid return. We do this by fitting an autoregressive with lag 1 rolling window observation. So here if your autocorrelation between time 1 and time 1 step behind is 0, it means there's not much memory and you return quickly. So where I am now was not really related to where I was yesterday. If your autocorrelation tends to 1, that means you really have a high autocorrelation and you are approaching a critical transition. So the issue with paleo is that mixing and core compression could really affect this time 1 autocorrelation. So we can see that if we're mixing between layers, the layers will become more similar, so it could spike the autocorrelation. If we're compressing, then we could erode it probably because we're kind of losing the resolution of time 1, time steps, lag 1, I mean. So with the simulation, we wanted to know if factors encountered in core mixing and compaction weakened our ability to detect critical transition. So we tested for false positive first, where we had a simulation without critical transition. And here we found that core compression alone did not cause an increase in the variance. So basically we had thought that maybe as we compress less and less the core towards the top, then we're seeing better and better, but with seeing more, we're also allowing more and more variability because we're kind of opening up that time frame. But actually it did not happen. So that was kind of like, okay, check, we're okay. But however, when we tested for true positive case, so test with critical transition, we found that mixing did increase the lag 1 autocorrelation and compaction eroded it. So just to show some figures of that, the top figure is just an example of a simulated core series where we had intermediate mixing and intermediate core compression, and where we generated a regime shift or critical transition at time 300. And then the lower panels are scenarios where we actually played around with mixing. So this is just one example in A, and then for the lower panels, we tweaked a bunch of we played around with the mixing and compression. And so when we look at the variance, whether or not there's a rise in variance as we approach a regime shift, critical transition, I'm going to stop saying what we saw was that mixing and compression did not affect the rise in variance that much. We don't really see a difference between the different degrees of mixing or compression, but we did see an effect on the rise of autocorrelation. So what we see when we go from no mixing to high mixing, that the autocorrelation increases. So each interval become more and more similar to one another, and they seem to be more correlated than they actually are. In contrast, when we go from low to high compression, when we had really high compression, we completely lost that signal. So it seemed like we didn't have a regime shift when we know we actually did have one, a critical transition. So I keep on saying regime shift, but I should be saying critical transition. I'm sorry, I'll eventually stop saying that. Okay. The last part of this is we simulated 100 different cores where we did this critical slowing down scenarios. So there was a critical change that took place, and the eigenvalue, the rate of change slowed down. And we did this with intermediate mixing and intermediate compression just to have kind of an average view of this. And what we found was that if we looked at the rolling window, and if we saw a rise in variance or a rise in autocorrelation, we actually saw that point where it did rise varied a lot. So basically, it just showed that these two methods were not accurate. And so the dotted line shows the mean of these 100 runs, and the black line shows the example that in the previous slide that we just saw. And so we see that there's a lot of variability between these different simulations. But on to other models to see if we could detect this regime shift and critical transition a bit better. So what we saw with the rolling window method, some of the shortcomings were one, that we can't account for higher order autocorrelation. So we can only look at lag 1. We can't look at lags of 2 or 3 or higher order lags. The choice of the window length is also arbitrary, and we can't account for rapid changes in this ability because our parameters, our coefficients are static. They don't change over time. So that's why we moved to dynamic linear models and time varying autoregressive state space models, because these models allow us to fit higher order autoregressive models, and they also allow for coefficients to vary over time. The two approaches are really similar. The latter one, it adds observation error in the data. So they are very similar. They have very different names, but they're similar, and they each have their own advantages and disadvantages. So that's why we essentially decided to run both, just to compare them and see how well these different models did. And so just to really show the difference between the rolling window and these dynamic models or these state space models. So the rolling window basically looks at where you are at one time as a function of where you were yesterday. The dynamic models have an extra part of the equation where they actually allow this coefficient, like your regression coefficient, to itself vary over time. And they're called sometimes the first one, we sometimes call it the online dynamic linear model, because as more data comes in, the parameter is adjusted. And so this allows your eigenvalue to change over time. And so the results of this simulation with the online dynamic linear model was that we were able to detect with our simulation the regime shift, so that the change in the intercept at the right moment. And we were also able to detect the change in the rate of change at the right point, and that this left the unit circle at the critical transition. So we see here that anytime we see the eigenvalue or its error bars exit the unit circle, that we have evidence of a critical transition when we're working in discrete time. The other method, the time-varying autoregressive model, also worked well. It was a bit more sensitive than the online dynamic linear model, but in general, they both did good. But as we increased the environmental noise and we had these scenarios where we flickered between alternate stable states, they both had a greater difficulty in providing the accurate timing of the critical transition. Sometimes it helped to move to higher order lags. But in general, when you have noisier records, you can't make miracles. And if there's too much noise, it makes it difficult to pick up the signal. So the last part of this project, before I move on to the multivariate approach, was that we applied it to 3 different lakes. So we applied it to a lake that had an abrupt and clean change, one that was noisy, and one that had flickering between alternate stable states. And in general, we were able to detect the regime shift in these models. Some like, for example, the noisier record, we could see that it approached, and so there was a lot of error, much more, and it was not as clean to detect this. And we also had to try different lags in order to fit the model. And we found that it was the best model actually was the one where we were looking at higher lags, higher order lags between time points. But with that, I just wanted to spend the last few slides on the last part of the talk on getting back to the key question and the motivation for this study in the first place. And it was to get to the question of whether or not nonlinear ecosystem responses are the exception rather than the rule. So are critical transitioning happening everywhere around the world, or are we just looking at specific lakes where they're actually taking place? And so the questions that we wanted to ask with this is whether outcomes vary, for instance, across lake types, so across deep versus shallow lakes. Are certain proxies better indicators of critical transitions? If we look at the community as a whole, do we get a better diagnostic than any one proxy? So there's more information available. Can critical transition be upscaled to the whole aquatic ecosystem? So this here, it's whether resilience indicators at one trophic level could be detected in other food web components. And finally, we wanted to, if we can, we would like to explore how multiple drivers, whether intrinsic or extrinsic, can interact. And so just to kind of bring in, to try and explain these critical transition as a response to a certain environmental condition. And what's nice is some of these state space model can handle covariance, and they allow you to tease apart the role of each driver over time. So that could be interesting. So I won't spend too much time on this, but for the multivariate approach, basically what we do here, instead of examining the one eigenvalue, we're now examining the leading or the dominant eigenvalue from a multivariate matrix of different species or different, whatever your matrix is that you're looking at that's multivariate. And so basically it's an extension of the models we just saw, but instead of being univariate, instead of having in the code just X as a vector, you now have X as a matrix. So it's the multivariate counterpart. And then you only retain the largest eigenvalue from the system. And I just want to mention that there's actually a paper now in review that Steve Carpenter and colleagues just wrote, where they actually apply this new method to look at resilience in a lake undergoing enrichment and as a function of both nutrient enrichment and dissolvable organic carbon enrichment. So hopefully, probably that will be out soon. So with this multivariate approach, what we would like to ask or be able to get to is which proxy is the lead indicator of the transition in a lake. So let's say you have a matrix of different phytoplankton. You want to know, are cyanobacteria the indicator, or is it diatoms, or which one is not diatom, but which algal group is the most important indicator, kind of like the canary in a mine. So to look at this, what we can do is the weights of these different proxies, or the eigenvalue of each one of these species on the leading eigenvector, and we show the contribution of each of these to that eigenvector. So you can think of this has an analogy to a PCA, where you run a PCA and the first dimension, the first axis is your eigenvector 1, your first eigenvector, and the weight of each species is the shadow that these species cast on that eigenvector or that axis. We could also look at the ratio of each one of the eigenvalue of each species or each column over the sum of all eigenvalues. And then for there, we can get to the relative contribution of each one of these proxies or species to any stability shift. So then on to many lakes, and instead of many proxies, I'm saying many pigments, because what we looked at again is some pigment stratigraphies that we had from a data set that from earlier studies where we had pigment cores across North America. And well, for today, I'm only going to present results from Canadian lakes, and they're very preliminary results. So here we examined for the lakes that we had whether a critical transition using multiple different pigments, so a multivariate approach, not hugely multivariate, but still not multivariate. So we examined whether a critical transition was detected, and which, if so, whether this took place prior to 1950, post 1950, or throughout the core. So we just chose 1950 really arbitrarily, because as in paleo, we often see that kind of hockey stick response, or in the Anthropocene, we often see an acceleration and explosion past around 1950. And so here's a map of the cores that we had. So you can see that there is definitely room for improvement in terms of spatial representation. There seems to be a spatial pattern where lakes that experience a critical transition were largely situated in the Canadian prairies. Then again, we also have more lakes there. So just to try and see whether or not these results could be explained by some kind of environmental driver, we just ran some simple box plots. And what we found was that lakes that had at least 50% agriculture in their catchment, that were hyper-eutrophic, and had a shallow thermocline underwent at least one critical transition throughout their history. And among these, shallow lakes in small catchments with long water residence time seem to have experienced a transition historically, so pre-1950. And what's interesting is that those with more recent transitions were the deeper lakes in large catchments with relatively faster renewal time. So, you know, it's hard to say how robust these are as we increase the sample size, but so far there seems to be an interesting pattern that's worth looking more into. And then to get to the last part, which I think is probably the part that I like the most about this, is the leading indicator. So here's an example of a lake with a critical transition. You don't see it on the axis, but it does cross one. And what we could do then is look at, so this is the leading eigenvalue, and we could look at the weights of different pigments, so different proxies. Here I just have three on this dominant eigenvector, so like kind of like the axis one of a PCA. And what we see is we were able to show that one of the pigment really goes kind of crazy after 1950, consistent with outbreaks of cyanobacteria, although I'm showing most pigments that are cyanobacteria, but still this suggests that this algal group played a big role in the breakdown of the stability of this lake. So it shows nice potential for applying this to more proxies or different kinds of proxies. So just to finish up on what to now, so just a little roadmap. So the thing we would like to do next is to gather more data for broader scale representation. And then also run some simulation on the multivariate approach for core records like we did with the first paper, just to make sure everything is working as it should. And then also rethink the classification of critical transition versus not. So for example, the map and box plot I showed, I only classified lakes if they really crossed the eigenvalue 1, but some of them hover closely above. So it would be good to develop some kind of confidence interval over that and have, is it truly crossing or is it just approaching? Although approaching is still interesting because it means that an abrupt change is about to happen. Then we also like to explore if the outcome depends on which proxies we're looking at, but also the number of proxies included. So we saw that as we increase more pigments, that the results varied a little bit, and it may be dependent on which pigment or maybe even the number of pigments or columns we included in the matrices. If we can, it'd be nice to include extrinsic or intrinsic drivers, but maybe we'll just stick to the box plot approach, which is still very nice and synthetic. And then finally, just finalize the paper, which is a huge step still, but that's the goal. And so with that, I just wanted to thank Steve Carpenter, who wrote wonderful code, had really inspiring discussion. I learned a great deal from, was always really rapid responses. Also wanted to thank my colleagues at Environment and Climate Change Canada, Conrad Beauvais, Maud Lachapelle, and Uda Hanna for helping and actually just doing the literature synthesis, data digitization, and creating really beautiful and very clean databases to work with. And lastly, to thank the working group, the Critical Transition Working Group, and the co-authors as well on the paper for generating the ideas behind the ecosphere paper that we published in 2018 on the univariate approach. And so on that, I thank you for your time, and just will take any questions if you have any. And I'll stop sharing.